Hi, my name is Adosizi, and welcome to the lab explanation video for Lab 1.3, Introduction to PyTorch. In this lab, we are going to be learning the foundations of the deep learning framework called PyTorch, which will allow you to build many different types of AI models and applications. To access this lab, you can go to the inspiredk.org website and click on the AI Program Labs button. This will take you to the inspiredk.org GitHub, where you can navigate to the MIT Intro to Deep Learning repository. The lab we are going to be going through today is adopted from the MIT Introduction to Deep Learning course, and I edited it under the MIT license. Once inside the MIT Intro to Deep Learning repository, you can navigate to the Lab 1 folder and click on the Lab 1.3 Introduction to PyTorch Python Notebook and the Run in Google Colab link in order to go through the lab on a platform called Google Colab, hosted by Google to offer free GPU access to anybody with a Google account. Now, let's dive into the lab by starting with downloading all of our dependencies, including PyTorch and its submodule NN for neural network layer access, the MIT Introduction to Deep Learning package, which was created by the instructors of the course to abstract away some of the more complex coding parts so we can focus on the deep learning experience. Then we also import NumPy for multi-dimensional arrays called NP arrays, and we also import Matplotlib for the graphical visualization of different statistics such as the loss. While the packages are importing, which will take about 2 minutes, I'd like to introduce the MIT Introduction Deep Learning package. It offers many different functions, and for this lab, we are going to be using the test custom dense layer output function, which will verify that the layer we will be creating later on with mathematical operations is performing correctly and will output the right results. Our packages are still importing, so now I'd like to introduce PyTorch, which is similar to the machine learning library TensorFlow, which allows us to work with multi-dimensional data types called tensors, which can have many different dimensions. We're going to start by creating 2 different tensors with a dimension of 0, including integer, which will be the value 1, 2, 3, 4, and decimal, which will be the approximate value of pi, 3.14159, etc. When we print each of these tensors, as well as their ndim, or number of dimensions, and what they are, we are going to be able to see that they are both 0-dimensional tensors, and our first tensor will be of the value 1234, and our second value decimal is going to be 3.14159, etc. As our packages are still importing, the code cell will be unable to run until these are done, and we will also be able to create 1-dimensional tensors by increasing the amount of items that we have inside of our tensor. With the Fibonacci tensor, we have a list containing the items 1, 1, 2, 3, 5, and 8, meaning it has 6 items inside of this tensor. Now that our packages are done importing, we can see back with our 0-dimensional tensors, they indeed had a dimensionality of 0 and were only contained as one value. In our 1-dimensional tensors, in addition to Fibonacci, we have the count to 100, which contains a tensor of all of the values from 1 to 100. When we print the ndim of the Fibonacci and count to 100 tensors, as well as their shape, we will be able to see that both of these tensors are 1-dimensional, and the Fibonacci tensor has a size of 6, as it only contains 6 items, and the count to 100 tensor has a size of 100 because it contains 100 items. Now let's take this a step further and create 2-dimensional as well as higher dimension tensors. We're going to start by defining a 2-dimensional tensor containing the entries 1 through 8 in a 2x4 dimensionality, and we will make sure that our matrix is being created as a tensor object and it has a ndim of 2. When we run this code cell, nothing is outputted and no errors occur, meaning our tensor is correctly created with a shape of 2x4, 2 dimensions, and containing all of the entries from 1 to 8. As an example of why we would need tensors in deep learning, let's take an example where we have 10 different 256 by 256 images with each pixel being represented as an RGB value. To create this, we would need a 4-dimensional tensor with dimensions for the number of images, the height and width of each image, as well as the number of color values for each pixel in the image. Now let's make sure that our image is a tensor, has a ndim of 4, and has the shape of 10 by 3 by 256 by 256. When we run this code block, nothing is outputted, meaning our tensor is correctly created as an image container for the 10 images that we have. In this example, all of the values are set to 0, but in the real world, all of those images would have a vast variety of numbers for all of the RGB values. Let's also use the shape of a tensor in order to slice it in different ways. Let's take our two-dimensional matrix of shape 2 by 4 from before, and let's get the second row at index 1 from this matrix. We can do this by using the index 1 on the matrix, allowing us to get that second row. Similarly, for the column, we can get the second column at index 1 by selecting all of the items in our matrix and then selecting the column at index 1 or the second column. To get a value at a specific place in our matrix, we can provide two different coordinates, such as 0 and 1. This will take us to the first row at index 0 and the second column at index 1. When we run this code to see what each of these row, column, and scalar values provides, our row vector has 5, 6, 7, 8, as that is our second row. Our column vector has 2 and 6, as that is our second column, and the scalar value is simply 2, as that is the value stored at the first row and second column inside of our two-dimensional tensor. Now, I'd like to introduce the concept of performing computations on these tensor values, and we're going to start with a simple example of simply adding two different tensors together. We're going to start by defining two different tensors, A and B, where A is a tensor of 0 dimensionality containing the item 15. Similarly, B is also a 0-dimensional tensor, and it has the value 61. To add these two tensors, there are two different methods we can use. First, we can use the PyTorch.add method, or we can use the plus sign operator. The reason that both of these work is because when PyTorch sees that there is a plus operator, it automatically overrides it with the torch.add operation to correctly have this plus operation be used on tensors. When we run this code block, we see that 76 is outputted twice, as 61 plus 15 is equal to 76, and both of the methods we use to add these items together would work. Let's consider a more complicated example containing several different operations on two different tensors. First, we're going to define a function that will take our A and B inputs and add them together to get a value of C, as illustrated in this block of the diagram. Then we're going to subtract our B value and 1 to get the value D, also illustrated in this block of the diagram. Finally, we will multiply the C and D values together to achieve our final E value, which is finally illustrated in this block of the diagram. Now that we defined our function using different tensor and PyTorch operations, let's take some example values of 1.5 and 2.5. When we define our function and we pass through that 1.5 and 2.5, we get an output of 6 because our first operation adds them together, and 1.5 plus 2.5 is 4. Our second operation adds the values it subtracts the values B and 1, which is 2.5 minus 1 equal to 1.5, and the E value multiplies C and D, which is 4 times 1.5, or the value 6. Let's take all of the knowledge we have working with these mathematical operations in PyTorch to create a simple neural network layer. At its most basic level, neural networks take an input of weights, inputs, and biases, and it multiplies the weights and inputs together and adds the bias to get a value of Z. Finally, this Z value is passed through a nonlinear activation function, such as Sigmoid, to achieve an output. Let's create our very own class in order to define all of these mathematical operations, and then we will pass an example input to see how it works. Our class is going to be called rDenseLayer, and we're going to define it with an argument of W, or the weights, and B, the biases. The shape of the weights will be the number of inputs by the number of outputs, and the shape of the biases will be the number of outputs, so these mathematical values can work correctly in the operations. I'd like to note now that the operation defining all of these parameters is completely random, meaning those values generated for the weights and biases will be random. Then we define our function of forward using the weights, biases, as well as an input of x, where we first multiply the x and w, or weights, and we add our bias. Then we can use torch.sigmoid for our nonlinear activation to pass this z value and get our final output of y. Now let's define our dense layer with a number of inputs of 2 and a number of outputs of 3. We define our layer and we create an example input containing the items 1 and 2 in tensor format. Then we can pass this input through our layer to get an output of y, and we can see the input shape, output shape, and the output of this layer. When we run the code block, we can see the input was of shape 1 by 2, which contains the entries 1 and 2 in a two-dimensional tensor. The output shape is 1 by 3, which we define with our number of outputs. And finally, the output contains 3 values in a 1 by 3 tensor based on the input and randomly generating the weights and biases to perform this operation and provide us with this output. Because we often use this dense layer in practice when creating neural networks, PyTorch has already created some default layers that do this similar operation. Let's use the Sequential API as well as the built-in PyTorch layers to create a neural network that does the exact same thing as our self-defined dense layer. We're going to define the number of inputs and number of outputs again as 2 and 3, and we will use the Sequential API with a nn.Linear layer, defining it with a number of inputs and number of outputs, and then we will take the output of that linear layer and pass it through a nonlinearity sigmoid to complete our dense layer. We can define this neural network containing the singular dense layer, and we can again use the same example input from before to see the input, output shape, as well as the output itself. We run our neural network on this input of 1 and 2, and we can see that, like before, our input shape was 1 by 2, and our output shape was 1 by 3. Additionally, our output is exactly the same, which we can expect because the randomization was set similarly for our custom-defined layer, as well as the new sequential. Let's also create a new custom layer based on the built-in dense layer, and we can also add our own custom operations. We're going to create the class linear with sigmoid activation to combine a linear and sigmoid layer like we did with our sequential, and we can define the linear layer with the number of inputs and number of outputs provided, as well as the sigmoid using its nonlinear activation. We can also define a function that will allow our model to take an input and provide an output by passing the input through our linear layer and passing that linear output through the final activation function to achieve our output. Let's again define this linear with sigmoid activation class with 2 inputs and 3 outputs, and pass in the same example input as before with the entries 1 and 2. However, this time, because our model is being defined in a new way, the outputs will be random every time the code is run. When we run this code, we can see our input is of shape 1 by 2, our output is of shape 1 by 3, and we receive the output, which contains 3 different generated values from our class that has a linear and nonlinear activation function. The reason that this custom definition of a model is so crucial is because if we need to, we can now add custom behavior. Let's say we want to create a linear layer that will only output the inputs that it was provided when a specific value is set to true. We can do this by defining our linear layer with a number of inputs and number of outputs and creating our passing forward function so that way it takes inputs and an isIdentity value that is automatically set to false. However, if this isIdentity value is set to true, the inputs will be returned as is. And if this isIdentity stays false, we will pass our inputs through the linear layer to achieve a new output. If we test this behavior defining our linear with identity class with 2 inputs and 3 outputs and using the same example input as before, we can test our model without and with the isIdentity function. when we run our code block, we get an error because I did not run this code block to define our linear with identity layer. And if we run that code block and now run this one, we will see that our linear output without the isIdentity parameter had 3 random values generated from our model by passing it through the linear layer. And our identity was simply passing out the input that it was given containing the values 1 and 2. So far, we have covered different ways to define tensors in PyTorch, including 0, 1, 2, and 4 dimensionalities, and we saw how we can perform different computations on tensors, including adding, subtracting, and multiplying, and we also defined several different neural network layers, such as a custom dense layer, using the sequential API, creating our own class with the sequential API, and also adding custom behavior to a linear layer. Now, I'd like to switch to the topic of automatic differentiation, which can be used with deep learning models in order to train them towards a lower loss and higher accuracy for a given task. Let's take the example of an input x that is a tensor of 0 dimensionality, and it is set to the value 3. Let's say that we square this value and store it in a value y, and we perform the dot backward operation on this y. Because we set our x input to have a requires grad value equal to true, when we perform this backward operation, we can compute a value called the gradient, which is the derivative of all of the mathematical operations that have happened to this x value until this backwards operation is called. If we store our gradient value inside of a value called dy underscore dx for the derivative, and we print it out, we can see that the derivative or gradient value is 6, which we expect when we know the gradient and derivative of the x squared function for the value 3. Let's take this gradient a step further and see how we can minimize a value using this gradient operation. Let's initialize a random value that is of 0 dimensions and is only a single value, and we will initialize it at that random point. Let's set a target value of x underscore f that our x value should reach eventually, and a learning rate that will change our x towards that target value. Additionally, we're going to set a number of iterations that we want to keep looping through to advance our x towards the target value, and create a history list to plot all of the x values for graphing purposes. In each iteration of our total iterations of 500, we are going to define our x in a tensor, compute a loss value comparing the difference between our x and the target value squared, and we will perform the dot backwards operation on our loss in order to compute the gradient value, and we will update our x value by multiplying our learning rate by the gradient and subtracting our input x through that gradient value. Then we can add our new x to the history list, and at the end of all of these iterations, we can print our final x value. We can also plot our history list with an initial value and target value to see the trend that we have. When we run this code, we can see that through the iterations, our value initially starts at about negative 0.16 and quickly advances towards a near 4 value at 3.9998. This process of taking an initial value and moving it towards a target value is called stochastic gradient descent, and this is often used in machine learning in order to take a loss value and train it towards a lower and lower value close to 0, so that way we can have a higher accuracy on a given task. Although many other methods for this have been developed, stochastic gradient descent is still most commonly used in deep learning. So in conclusion, today we covered the different PyTorch methods that we can use, including importing the PyTorch library, seeing how we can create different tensors of 0 dimensions, 1 dimension, 2 dimension, 4 dimensions, and more. And we also looked at how we can slice different tensors by using their shape. We also saw how we can perform different computations on these tensors by adding them together, subtracting them, multiplying them, and more. We also looked at how we can take these operations and create neural networks, including a dense layer that takes an input and passes it through a linear and nonlinear activation. We also saw how we can use the sequential API with built-in PyTorch layers to perform this without having to customly define it ourselves, and we saw how the custom and non-custom definitions were the same. We also created a class using that sequential API to have a linear and nonlinear activation, and then we added our own custom behavior to a linear layer to illustrate why it is so important to have this ability to use PyTorch with different classes. We also examined automatic differentiation in PyTorch using gradient values and stochastic gradient descent in order to optimize a given value initially towards a target value, which can be used in machine learning to take our loss towards a value of 0. I highly encourage you to go through this lab so you can gain a deeper understanding of the PyTorch library and how you can implement it in code. Again, to access the PyTorch lab, you can go to the inspiredk.org website, click on the AI Program Labs button, which will take you to the inspiredk.org GitHub, and you can navigate to the MIT Intro to Deep Learning repository, click on the Lab 1's folder, and the Lab 1.3 Introduction to PyTorch Python Notebook, and the Run in Google Colab link to go through the lab and gain a deeper understanding of the PyTorch Deep Learning Framework. Thank you for joining me in this lab explanation video. Goodbye!